My name is George Phillips and this is my partner David Curtis. We are fourth year engineering students at Wits University. We are investigating a compact gain measurement chamber as an alternative to anechoic chambers for taking repeatable gain measurements. Anechoic chambers are expensive in that they require expensive absorber foam, calibrated antennas, and require a lot of floor space to be constructed. The compact chamber, on the other hand, is constructed from laser cut wood panels. This allows it to be set up in any location desired. It furthermore makes use of the single antenna method, which has significantly reduced space requirements.
The single antenna method is analogous to the two antenna method using a transmit and a receive antenna. The single antenna method requires half the space of the two antenna method by placing a reflector in the middle of the two antennas, effectively creating a mirror of the transmit antenna. This allows a single antenna to transmit a signal and measure the received power. The gain is then calculated using the ratio of the transmitted to the received power. This is our compact box. It is a 1 meter cubed wooden chamber. To perform a measurement, we place an antenna at one side of the chamber and then take a free space measurement for the S11 of the antenna. Once that is done, we then place the reflector at the other end of the chamber and take a reflector measurement, measuring the S11 with the reflector. In order to characterize the performance of our chamber in terms of repeatability and accuracy with our measurements, we investigated how the drift in the VNA could affect our measurements in the chamber over an extended period of time or with the equipment heating up. In the Wits anechoic chamber, we assessed whether different types of materials for the chamber walls could affect reflections inside the chamber. We studied flat absorber foam, solid walls, and walls with holes. From our measurements, we concluded that wooden walls with holes gave us the optimal performance.
We then studied the sensitivity of the measurement to the angle of the reflector relative to the antenna. This was once again performed in the anechoic chamber at Wits. The setup of the experiment involves placing the absorber perpendicular to the antenna and shifting the angle of the antenna relative to the reflector. We then studied the sensitivity of the measurements to different distances between the antenna and the reflector. This is done in the compact chamber simply by sliding the antenna to the desired distance and taking a measurement. We finally studied the effects of absorber material in the chamber to see whether or not it improved results. Previous results did show that flat absorber causes more reflections than the wood. However, we were limited to using flat absorber as conical absorber was too large for the chamber. We placed absorber on the ground underneath the chamber to see whether or not this would reduce reflections coming from the ground. We then placed absorber on the wooden floor of the chamber to see whether or not we could reduce reflections coming from the ground and from the floor. Our results showed that placing absorber on the floor of the chamber or on the ground did not drastically improve results.
We found that the method of time-gating allows us to remove a lot of the unwanted noise present in the data. We implemented a GUI into MATLAB that firstly allows us to process data as seen here on the left. The GUI also allows us to implement time-gating. This is done by taking an inverse Fourier transform of the S11 parameters and plotting them in the time domain. Observing the signals closer shows that from approximately 3 meters to 8 meters, the signal with the reflector, shown in black, differs from the signal taken in free space, shown in grey. The distance here represents the path the signal must travel before it is reflected back to the antenna. We can then apply a gate from 3 meters to 8 meters and enable time gating. We can then see how this portion of the signal looks in the time domain, and then compare this to the signal without time gating. As you can see here on the top left, time gating improves the gain measurement by removing the unwanted noise present in the signal.
We will now have a look at the different results obtained from the various experiments we performed. This graph shows the results from taking tests with different wall materials in the Wits anechoic chamber. As we can see, the walls with holes cut into them performed better than both the solid wooden walls as well as the walls with absorber foam on them. For this reason, we decided to cut holes into the wooden walls of the chamber and make that the walls of our chamber. Experiments where the antenna is placed at different distances to the reflector show that there is a change in gain measurement when the antenna is placed at different distances, with the antenna being closer to the reflector giving the more accurate result, as seen here. These results show the sensitivity of the gain measurement due to the angle of the reflector relative to the antenna. From these experiments, we can see that rotating the reflector by small angles can have a change in the gain measurement by about 1 dB. This allows us to conclude that the gain measurements are sensitive to small angle deviation in the reflector position. We can see that when the antenna is placed 90 centimeters from the reflector, it matches closely with the gain measured in a proper 2-antenna anechoic chamber. The gray region shows the error band of the anechoic chamber, which has variations of plus minus 1 dB.